So electric field and capacitor assignment for starting with question 1. Some spider may be seen suddenly moving up in air even when there is no wind. This happens when they let out strand of web. The spider are pulled up as the electrically charged strand of a web interact with a earth electric field. The average strength of the earth electric field is about 120 volts per meter downward. State with a reason the polarity of the charge on the strand of web. So what will be the polarity of the charge on the strand of web? As you can see, the average strength of the earth electric field is 120, which is downward. So this is the direction of the electric field. So if there is a positive charge, the positive charge will move downward, because the direction of the electric field is same as the direction in which the positive charge or a test positive or a unit positive charge experience a force. So what should be the charge on the string? Because it is being moved up, as you can see, some spider may be seen suddenly moving up in air even when there is no wind. This happened when they let out strand of a web. So when they let out strand of a web, that is moving, the spiders are moving upward. So what will be the charge? Because if it was a positive charge, then it should move in the direction of the electric field, as the electric field is given downward. But because it is moving opposite to the direction of electric field, so it means it is a negative charge. So the charge is negative because the direction of electric field is a direction in which the positive charge experience force, but this is moving in, and the negative charges always move opposite to direction of electric field. So the polarity of the charge on the strand, that will be negative. And what is the reason for that? Because it is moving opposite to direction of electric field. So if the strand moves same as the direction of electric field, it means it should be positive. But because it is moving opposite to the direction of electric field, that's why it is negative. And in part B, the spider moves upward after letting out a strand of a web. Determine the initial upward acceleration of a spider. The mass of the spider and the total charge on the strand of the web is 3 exponent minus 7. And the strength of electric field is also given, which is 120 volts per meter. So we have the electric field, we have the charge, we have the mass, we need the acceleration. So first what we will do, because we will use a formula, F is equals to ma. So force divided by mass is equals to acceleration. What force? Because the strand of a web is considered as like it is a charge object. So force on the charge object, we'll use a formula E equals F divided by Q. So F equals E multiplied by Q, where E is the strength of the electric field, which is 120 volts per meter, and the charge, the total charge is 3 into 10 to the power minus 7. So this will give us the force experience, and after getting the force, this will come out as 3.6 into 10 to the power minus 5 newtons. So we have the force and we have the mass. So force divided by mass, we'll calculate the initial acceleration. But like here we need a resultant force. So to get the resultant force, as the spider web, the strand of a web is moving up and the weight of the spider is acting down. So weight will be the downward force and the electric force is there that is acting upward. So what we will do, we'll find the resultant force by the difference of the two. So resultant force will be electric force minus the weight will be equal to resultant force, and that is equals to ma. Because this is a resultant force, not the force acting, it's the result of the two or more forces acting. So to get the resultant force, so how we can work out, as we work out the electric force, which is 3.6 into 10 power minus 5, and then we will work out the weight, the downward force, which is mass multiplied by gravity. So mass is 3 exponent minus 6 and the gravity is 9.81. So when we multiply them, we'll get the weight of this, that is 2.94 into 10 power minus 5 Newton. That's the weight of the spider. So the electric force is upward and the weight is downward. So resultant force will be equal to ma. And so electric force minus the weight is equals to ma. So we'll substitute the values. Electric force we already calculated, that was 3.6 into 10 power minus 5 minus 2.94. The weight is 2.94 into 10 power minus 5 equal to mass of the spider, which is 3 into 10 mass of the strength of web, that is 3 into 10 power minus 6, and acceleration we don't know. So we subtract and then divide. So the initial acceleration will come out as 2.19 meter per second square. So it is related to the first part because as the spider moves upward, letting out a strand of a web. It is letting out the strand of the web, and the weight is of a strand is acting downward. Electric force on the strand of a web is acting upward. That's why we calculated the resultant, that electric force minus weight is equals to ma. Is it clear? For any question, if you want me to repeat, I'll repeat that. Another, the earth has electric field because the charge is distributed over the surface. So over the surface, the charge is distributed. Determine the quantity of a charge on 1 meter square earth surface, which would cause an electric field strength to be 120 volt per meters. You should assume that the charge is distributed evenly and the radius of the earth is 6,400 kilometers. So like this is the earth. The strength of the electric field at this area of 1 meter square area, it's about 100 and that's on the surface. So it's about 120 volts per meter. And the distance, like the radius of the earth, that is 6,400 into 10 power 3 meters. So first, we will use this strength and we'll find what is the total charge. So strength of electric field at any point is given by a formula E is equals to kq over r square. That's a formula to find. Like example, if we want to find the strength of electric field at certain point, say that point is at distance r from the center. So we will use the formula that E is equals to K, the Q, the charge, and over R square. So source charge is there, R is a distance and K is a constant which is having a value of 8.99 exponent 9 or 9 exponent 9. And then what we will do after getting this charge, we need a charge on unit area. So how to work out area? Then we have to use area of the cross section, which is 4 pi r square, where r will be the radius, because we'll work out the total area, which will be equal to 4 pi r square because it is a sphere. So area will be 4 pi r square. So after getting a charge divided by area, we'll get the final answer for this. So this is the strength of electric field. The radius is given. Using the radius, first we'll find the strength of like the charge. So we have the formula E is equals to KQ over R square. Or if we need Q, it will be E R square over K is equals to Q. Where E is a strength of electric field, which is 120. R is a distance from the source, that is equal to 6,400 into 10 power 3 divided by the constant, which is 9 exponent 9 or 8.99. So using this, we work out the charge. So this total charge will be equal to 5.47 into 10 power 5 coulomb. That's the total charge. But we need charge on unit area. So how to work out the area? Area of a sphere, 4 pi r square. So we'll substitute the value. So charge divided by area, the charge is equals to 5.47 into 10 power 5. And area is equals to 4 into 3.14 into r square. Where r is a distance, so it will be 6.4 into 10 power 6 and then whole square. So when we divide them, we get as 1.1 into 10 power minus 9 coulombs per meter square. As they ask that determine the quantity of a charge on 1 meter, because when we work out the total area, like total charge divided by total area, so we'll get how much charge is there in a unit area. So quantity of a charge on 1 meter square area means quantity of a charge in unit area, or we need charge divided by area. So we work out the charge by using the formula of electric field strength, and area is 4 pi r square because it is a sphere. In question 2, a student is designing a night light for a child. When switched on, the night light should come on brightly and its intensity should then gradually decrease to 0. So this is the design of the circuit. Like student connected a capacitor, a 12-volt battery, discharge resistor is there, and light emitting diode is also connected. The time taken for a light intensity to decrease to 0 should be close to 10 minutes. Like student want this to discharge in 10 minutes, and the time must not be less than 10 minutes. So it should not take less than 10 minutes. What will happen? Like first, we have a 12-volt supply, so all the voltage will be there across the capacitor. When a switch is changed, we change the position, the capacitor start to discharge. So then this 12-volt will be divided between the resistor and the light emitting diode, and eventually the voltage of the capacitor decrease, so distribution or division of the voltage decrease, and eventually it will be like less than the operating voltage of a LED or 0, then the LED or light emitting diode will switch off. And it should take about 10 minutes to, or more than 10 minutes to switch off. The student uses a light emitting diode and a resistor. The LED stop emitting light. So the LED is not emitting out light. When the potential difference across it falls to 1.4 volts. So when the voltage, like As I mentioned, there is always an operating voltage, like a voltage at which the light emitting diode works. So when it reaches 1.4, it does not work. The student assumed that the LED has a constant resistance of 340 ohms. The capacitor with the following capacitance are available. We have zero point 0.5, we have 0.51, we have 0.54, 0.58, and zero point 0.6. Determine which capacitor student should use. So how will determine which capacitor which student should use? So normally the charging or the discharging time, like when we try to solve, we have the formula V is equals to V naught e raised to power. So voltage across the capacitor, like the LED stop emitting light when the potential across it fall to 1.4. So means the minimum voltage can be 1.4 across the LED. And what about the maximum voltage or initial voltage across LED? The resistance is 860. So if we have a resistance of 860, like this is 860 ohm, this is 340 ohm. They have the constant fixed resistances. So if initially it was 12 volt, so what will be the starting voltage? How we work out? We can use a potential divider formula, like V1 is equals to R1 divided by R1 plus R2 into combined voltage V. So if I need a voltage here, that is R1 divided by R1 plus R2. So 360 plus 860 plus 340 multiplied by combined voltage 12. And what about this one? 340 divided by 860 plus 340, the total resistance of circuit multiplied by combined voltage 12. So the maximum value, like when we solve 340 into 12 divided by 1100, because 860 plus 340, sorry, 1200, not 1100. So this 12 will cancel, so 100, so this will be 3.4. This is 3.4, this will be 8.6. Means when the capacitor, when we change the position of a two-way switch, like this is a two-way switch, when we change the position and the capacitor start to discharge, the starting voltage will be 8.6 for the fixed resistor, and the starting voltage will be 3.4 for the capacitor. And then what will happen? Because the total voltage across the capacitor start to decrease, so the total voltage across fixed resistor and the light emitting diode will also decrease. But what is the smallest like operating voltage? As I mentioned, once it reach 1.4, the capacitor will stop working. Like sorry, the light emitting diode will not work. And the charging or the discharging of a capacitor are exponential. So we will use a formula because the capacitor is discharging through this fixed resistor and LED. So V is equals to V naught e raised to power minus T over RC, where V is the maximum voltage. V naught is the maximum voltage. V is a voltage at a certain time interval, and R is a resistance through which the capacitor is discharging, which will be the sum of the resistance of both. So the initial voltage across the, because we want to find when the voltage changes from 3.4 to 1.4, because initially it is 3.4 across the LED light emitting diode, and then it reduced to 1.4. So it will start at this point and it will stop at this point. So V equals V naught e raised to power minus T over RC. And what, because we want the time, like we want it to work for 10 minutes, so time interval for start to stop should be equal to 10 minutes or 600 seconds, because it will be 10 minutes multiplied by 60 to convert into seconds. So V is a voltage at which the LED stopped working. Maximum voltage was 3.4. E raised to power minus T is a time for the capacitor to discharge. Like the basic idea that it took 10 minutes or 600 seconds to change the voltage from 3.4 to 1.4. And R is a resistance, but that resistance is a resistance through which the capacitor discharges. So what is the total resistance of the circuit through which the capacitor is discharging? 860 and 340. So when we sum them, it will be 1200. And multiplied by C, the capacitance. Now we simplify 1.4 divided by 3.4 and take an anti-log of this. Like this will go there in division. So 1.4 divided by 3.4 is equal to e raised to power minus 600 over 1200 into C. And then taking anti-log both sides. So when you will take an anti-log, you will get the value for capacitance, which is about 0.56. So which capacitor, when we solve, which capacitor we should select? Now, like this is approximately 0.56. So is the value of the capacitance which we should select. So we have the capacitance ranges. Determine which capacitance the student must use. And the capacitor with the capacitance which are available here, these are the available capacitors. So like 0.56 is giving a 10 minutes time, but we don't want to reduce the time. It should not be less than 10 minutes. It should be more than 10 minutes. So 0.5 is the minimum value. If we select less than, like if we select a capacitor with a capacitance 0.54 farad, then it will take us less than 10 minutes for LED. So we should select a bit, like 0.56 is giving us 10 minutes, but we want more than 10 minutes, not less than 10 minutes. So next one after 0.56 is 0.58. So we should select the capacitor with a capacitance 0.58. Is it clear? This question that how we worked out the value of a capacitance needed so that this LED will work for approximately 10 minutes or more than 10 minutes, but not less than 10 minutes. Then in practice, the resistance of LED does not stay constant. The graph shows how the current vary with the potential for the LED. Explain how the behavior of LED shown in the graph will affect the time for the light intensity to decrease to 0. So here you can see the small change in potential, but greater change in value for the current. So it means from the graph, the potential decreases greater than, so as the potential decrease, so from 1.4, like usually its resistance not changing, but when you can, like if it was a straight line, so this is 1.4 and this is 3.4, the potential. So if it was discharging, like if the resistance was constant, then it will be a straight line. But now what is happening? Like it will take a longer time to change from 3.4 to 1.4. So as it will take longer time to change from 3.4 to 1.4, it means the LED will light up for a longer period of a time. So from the graph, as you can see, the potential decreases and therefore the time constant will increase. So it will take longer time to switch off. As the graph between the current and the voltage the potential, if this was a graph like potential difference and current, so if it was a linear relation, then it will change from 1.4 to 3.4 or 3.4 to 1.4 because initially the voltage is 3.4 and then it is decreasing. So it will change from 3.4 to 1.4 in a short time. But because it is not its resistance is changing, and remember, like the value, because the current and potential graph slope is reciprocal of R. So if the slope is increasing, it means the change in the resistance is greater. As a result, as the potential is gradual, like potential across it, it is increasing, but it will take longer times. As a result, when it will take longer time, means the LED will light up for a longer time. So from the graph, we can determine as the potential is decreasing, the resistance is increasing. Like if the volt, because this will be 3.4 and this is 1.4. So as the potential start to decrease, it is not a straight line, it is a curve. So if the potential is decreasing, and you can see here the gradient. So gradient, like in the angle with x-axis, the gradient is there. So what happened from 3.4 to 1.4, the slope is decreasing. If the slope is decreasing, it means the resistance increase. If a resistance increase, like capacitor will take longer time to discharge or LED will light up for a longer period of a time. So you can determine from the value for the of the slope. The students state that a capacitor is being used in this circuit. The function of a capacitor is to store electric charge. Explain why this is not a complete description of the function of capacitor. Remember, capacitor cannot refers to store electrical charge because overall charge on the capacitor is zero. Capacitors actually separate the charge, but the net charge on the capacitor is zero. How? Like if we have the parallel plate capacitor, when we connect the battery, so this one side is connected to a positive terminal of the battery and the other side with a negative terminal. So towards the positive terminal, the charges are attracted or removed. So there will be a positive charge on one plate. And from negative terminal, the electrons start to flow. So majority of the electrons will be here or negative charge here. But overall charge, because it is 3 positive and 3 negative, so what is the net charge? Plus 3 and minus 3, it means net charge is 0. So capacitor cannot be used. We don't say capacitor is used to store charge. We say capacitor is used to separate the charges and store electrical energy. But we never say capacitor store charge because the overall charge or the net charge is 0. So the complete, why this is not a complete description because the capacitor, the net charge is 0. It is used to store, it is used to store electrical energy and separate the charges. So that is the main use of the capacitor. But we never use a term that capacitor is used to store the charge. We say it is used to store the electrical energy. The diagram shows a part of a spark coil. So this is working. The working principle is electromagnetic induction, like change in magnetic field. Like there is an alternating current which magnetizes the iron core, and due to change in magnetic field, EMF induced in the secondary coil. The spark from when the electric field strength in the gap exceed 3 exponent 6, so that air become conducting for a short time. Different spark coils produce different potentials. As you can see, maximum gap is there at different potential. Explain how the data in the table shows that the field in the gap is non-uniform, means it is not a constant electric field. How it shows that the electric field is not constant. So when we work out the value, because the strength of electric field between the parallel plates is given by, we have the formula V is equals to ED. So E is equals to V divided by D. So when we divide like 110 kilovolts by centimeters there, so it will be 10 into 10 to the power minus 2. And then we divide 150 kilovolts by 20 centimeter. So all these values will not, like all these answers won't be same. It will give a different value. So that's why it shows that the strength of electric field is not constant, because strength of electric field between the parallel plates is given by V divided by D. So the ratio V over D is not constant. Like 110 divided by 10, so it will be 11 here. But 150 divided by, it will be 7.5. 30 divided by, 190 divided by 30, that is 6.33. And 230 divided by 40, that is 5.75. So the strength of the electric field is not constant, as the values are not coming out same. But better convert the units like kilovolts in centimeter into SI volts and meter, and then use the value. Sketch electric field in the gap. So electric field is always pointing from positive to negative. So we'll draw electric field from positive to negative. The strength of electric field as we move away, that is decreasing. So when we draw a pattern, and the arrow is also important to draw, it's always from positive to negative. So this is a value, like this is a direction of the electric field. Then there's another circuit